Hello everyone and welcome back. Right now we are looking at the longest common subsequence problem, which is in fact a very popular question and it has a lot of variations as well. Some of the standard ones involve longest repeating subsequence, edit distance, longest common substring. Now in this video, our sole focus will be on solving longest common subsequence problem. We are not going to give any regards to other variations in this video. We will make sure that we have a proper understanding of the base that is longest common subsequence. However, if I am going to make videos on its variations, watching this video will be the top priority prerequisite for it. So, the aim is set that we want to understand and in fact develop the code for the problem longest common subsequence. So very firstly, we want to develop a flow for solving this problem. First of all, we will understand what is sequence. Moving on, we will understand or see what is common subsequence. And now we know what is common subsequence, we know what is longest common subsequence, we understand that. So at third, we are going to develop our approach, which is going to be dynamic programming approach, as the name of the series of this YouTube tutorials suggest. And the fourth, at last, we are going to look at if there is any more efficient method for solving this problem. So now what is a subsequence? And if you already know that, feel free to skip this section. So I'm going to take an example of A, B, D, E as a string sequence. And if I am supposed to define its subsequence, if I move from A to left to right, either I can choose one or not choose one. ABD, A, B, E are subsequences. ADB is not because I'm going A, D, B. DB is not the order from left to right. DBA, no, when I go from D, I can only move towards right. So D is proper, but ED is not a subsequence. Now if ABD is a string or subsequence, and another subsequence we have ABCD, and I'm supposed to list out all the possible subsequences of these two sequences, maybe I can look into what are the common subsequences we have. And once I can look into the common subsequences we have, I can point out the longest among them. So starting with every sequence is a subsequence of itself. So ABD is also a subsequence of itself. ABD, ABE, AB, AD, I am just listing out all the subsequences AE, BD, then BE and then DE, and at last we have AB, DE. These are all the subsequences possible for the string or sequence ABDE. For ABCD, the first subsequence will be itself, that is ABCD of length 4. I am doing it in decreasing order of length. So again, as it was for the previous one, AD, BC, BD, CD, ABCD. These are the list of subsequences for the sequence ABCD. Now I'll quickly just mark out some of the common subsequences I can see matching. So ABD is definitely one of them. I can see AB being a common match. Then definitely AD is there, BD is there, A, B, and then D at last. So these are the list of common subsequences we have. And what I want is the longest common subsequence. So definitely it is at the top, that is ABD. So we have solved our problem and this can be our approach, but when you go to programming, listing out all the permutations that are possible, I mean it permutations, not just combination, because order is important, and then seeing which matches is a huge task and it is going to like forever. So it is a very naive approach. What is a naive approach actually? Once we list out the permutations, what we are going to do, in order to optimize further, what we will try is we will try to develop a frequency counting dictionary where we count the number of frequency of each letter, and if they are same, we are going to say we have found our longest common substring. But that is also not a match, not a solution, because ABD can be BDA, and then even though the frequency is same, order is different, they are not a matching subsequence. So frequency counting is flawed. We can't even use frequency counting even when we have used exhausted so much of time into listing out the all common subsequences. We can't even now apply frequency counting to at least optimize in the further step. So order of letters is important, and our approach is flawed. So our intuitive approach is flawed, and we have now so far progressed. We have an understanding of subsequences. We know what is common subsequences. We know how our intuitive approach is at best too exhaustive in terms of time, and if not, it is going to be flawed. So now we are left with nothing but to shift our mindset to looking at the problem with a dynamic programming kind of mindset. So now we are disclosed our problem statement, and it is nothing new. It says given two sequences, find the length of the longest subsequence present in both of them. So we are given two strings which are our sequences, and we are to print the length of the longest subsequence possible. As an input, the first string we are given is ABCDGH, and the second string that we are given is AEDFHR. So without looking at the table that we have at the bottom, when the time will come, I'll explain why I have drawn it and how we are going to use it. So without looking at it, what we have is two strings and output is 3, so I can see this common subsequence can be ADH because it is visible to me that it is present in both the strings. So how did we exactly actually visualize that ADH is the longest common subsequence? So what we actually did is we had our string 1, and for string 2 we saw that A is matching A, good for us, and then we knew that the next match is D. So what we are going to do is, as we write the string 2 AE, instead of writing D, I insert and skip. So with respect to string 2, I am skipping the next, I am putting a blank, and with respect to string 1, I have inserted C. Let's not talk about relativity of which string we are working with. Let's focus on relative to string 2. So I have skipped, instead of entering D with below C, I skipped that place and I inserted D at the matching place. Then moving on to F, I inserted F below G, and then I inserted H below H at the matching place. And in place of a dash or blank, because there is nothing after H, I inserted. This time I didn't skip, I inserted an extra letter. In place there was nothing, so I was inserting with respect to S2, and with respect to S1 I did a skip. So whatever we did, it is not clear, but it is clear that we did something insert, something skip, something match. There was a match condition, there was a mismatch condition. So what was the mismatch condition? I'll quickly point out. B and E were not matching, but we placed it anyway. F and G were not matching, but we placed F below G anyways. So there were 4 operations that were taking place. We might not yet have the complete understanding or any understanding at this point, but we saw there were 4 operations taking place. So now we have this DP table, and I have drawn it already so that we can save time and focus on the approach instead of drawing this table. So let's keep it slow. It is nothing but a table of n cross m, that is length of string 1 cross length of string 2. This table is of m cross n dimensions, m along the y-axis and n along the x-axis, and we have along those axes, I have done 1 indexing, not 0 indexing, 1 indexing, and each index represents a letter of the sequence. So along the x-axis, along the y-axis, vertical down, I have string 1, and along the x-axis horizontally placed I have string 2, that is AEDFHR, starting with 1 indexing 1. Similarly, I have done the vertical arrangement for string 1. And basically what I'm going to do is computerize the insert and skip, match and mismatch logic that we saw in mathematical terms. And it is, believe me, a very simple formula, but is difficult to digest at first, and we are going to keep our pace slow. We are going to slow down here a bit, and we are going to take things slow so that in order for you to understand it in your first attempt. So like any other DP table, we initialize it with some values. So at 0 indexing, I'm just going to enter 0 elements to all the table elements that occur at 0 index, either at I equal to 0 or j is equal to 0. So if the column is 0 or the row is 0, it doesn't matter, I'm going to put 0 because we are playing 1 indexing, we are not playing 0 indexing. So 0 is nothing but empty, I'm going to keep it 0. 6 is nothing but length that we have, that is n plus 1, but actually the length is 6, so it's not n plus 1. In Python I'm going to range it from till n plus 1, but I have kept it from 0 to n, including n. So n is nothing but the length of the strings that we have. So now we are going to iterate in a row manner, row by row. So in each row I am going to iterate each column. So the first element that we are iterating is 1, 1, and that represent A in string 1 and A in string 2. And since A and A is a match, I'm going to do the mathematical equivalent of match, and that is nothing but the element in the diagonally upwards leftwards column plus 1. And what does that mean? And I'll quickly explain that. So first of all, if we found a match, what we did is dpij is equal to, that is dp11 is equal to dpi minus 1 j minus 1, that is dp00 diagonally leftwards upwards plus 1. We did this. So just to be clear, what we actually did here is written in the formula at the bottom. But why we did it? We need to understand it, right? It was done because whenever there is a match, what we are supposed to do is we are supposed to shift each string character to the next. We are supposed to shift each string character to the next because there is a match. Now we will visualize it and understand it. What do we mean by shift each character? We are coming diagonally downwards. So we did shift along right side, that is we shift in string 2, and we did shift vertically downwards, that is we shift to next character in string 1 as well. So that is what I mean, that we shift by each character in each of the strings. That is what we do in a match situation when we face a match. Now, as I said, I will iterate in a row-wise manner, and in each row I am going to iterate in a column-wise fashion. So we are now on dp1, 2, shifting rightwards column-wise, and our elements are A and E, which is a mismatch, not a match. So what are we supposed to do? Let's check out. So whenever there is a mismatch or a skip operation taking place or an insertion operation taking place, or if it is the mismatch operation taking place, whatever is taking place, on the top of it what we see is it's just not a match. So dpi, j, in that case what we do is we take the max of dpi minus 1j vertically upwards and dpi, j minus 1, that is horizontally leftwards. Now why are we taking this? Again, a good question. We need to understand it. So what we are trying to do is we are trying to pass on the optimized result, that is as far whatever we have the optimized longest subsequence length stored in our DP, we are going to pass it on for future use. So in fact this operation is in a secrecy doing the skip or insert operation, And now we are going to visualize it and have a look at it. So over here at I minus 1 comma j, I have 0, and I comma j minus 1, I have 1. Now of course the maximum of the two choices we have is 1. So we are going to take that 1 from the left side and put it in our current cell. So we are just passing on the previously optimized result, and what is happening is we have AE as a string 2 and the other string is A. We have moved shifted rightwards, that denotes we have shifted to the next element in string 2 that is at the top placed horizontally, but we didn't move down. We just, our j value didn't go down. I value, I'm sorry, our j value shifted, but I value didn't shift. We are not shifting row wise this time. So A remains as it is. We didn't move to B, but we moved to E. What does that represent? We added a blank. We skipped. We added a blank below E. We didn't place any letter from our string that we have on the vertical edge. But what will happen as we move on? For D and A, there is not a match. So we pick up again the maximum choice we have, that is available 1 towards our left. So again we move rightwards, but not going down, we are moving right. So again we are placing a dash. And that is how we visually are moving along the column. Along the row, what we will be doing is putting a dash on the string above us that is placed horizontally, and which will be with respect to our vertical string and insertion operation. So I hope that gave you a visualization of how things are working. Now I'm going to undo it and keep the table back to its neat form and just summarize what we saw. What we saw is that if we move rightwards along the table, what I'm talking about with respect to the string we have on the left side vertically placed, what we are doing is skipping character from string 1. String 1 is placed vertically on the left side, and if we move, so string 1 is on the placed vertically on the left side, and actually I would like to give this conclusion a little bit of more space. So if we are moving rightwards along our table, what we are doing is we are skipping character from string 1, and string 1 is along y-axis, that is vertically placed. So with respect to it, we are skipping a character, and we are moving downwards. We are going down the table. What we are doing is we are skipping character from string 2, and that is nothing but the string that is placed horizontally along the x-axis. And when we are going rightwards, downwards, diagonally downwards, well, you know it, we are not skipping any of it. So that is the case for match. Now I'm going to quickly fill it up. So each time it is going to take the maximum of the choices it has unless and until it meets a matching situation where the characters are matching. So I'll just quickly fill up the table until and unless I encounter a case where the characters are matching. So now finally we are encountering our second matching situation where D is matching D. So for a match, what we are going to do is we are going to shift each character in each of the string, and how do we represent it on our table? That is, we go diagonally downwards and add 1 to the element that is placed diagonally upwards. So element placed diagonally upwards is 1, and I'm going to add 1 to it, and now 2. So 2 is nothing but length of the longest common subsequence so far, and that is AD. And now again we are just going to keep taking the maximum choices among the two choice we are going to get every time, and it doesn't matter if both the elements on top and left are equal. It doesn't matter which way we come from, it's just taking the optimum possible. So it should be 2 there. Okay, 2. And H again is a match over here. So how do we show match in a table? Diagonally downwards, and it is going to be for this time 2 plus 1, that is 3. And now again we have possible choices 3 and 2. 3 is maximum, we are going to take it over 2, and this at the bottom right is our answer. We have exploited the entire length of the sequences, and we have reached dpn or m comma n, dpm comma n if the length of strings are different, and m comma n is nothing but the length of the longest common subsequence. And clearly we were using previously optimized results to optimize results further, so it was a dynamic programming approach which mainly consisted of just 2 formulas. Even though it was hard to understand, formulas were straightforward, single line, 2 formulas. And once we know why and how the visualization of the table works, that we have that feeling, the logic, the formula is just a straightforward formula. So again, the entire problem was based on just 2 things. One, if the elements do not match, and the other, if the elements match. The characters of the string match. Just 2 cases we needed to look for, and that was it. O of n square was our approach, but if there is there any more efficient method, we did it in O of n square. Is there any more efficient method? The answer is no. There is none other method that can solve it faster than O of n square in the worst case scenario time complexity. So dp is the most optimized solution we have for this question. And other than that, I would like to discuss one last thing is, now we know that what is the length of the longest common subsequence. Can we print what is the longest common subsequence? That is, can we print the answer A as ADH? How do we do that? We will be using backtracking. So it's just a hint. I'm not going to explain it or show it to how we are going to backtrack it. We just need to look for the diagonal operations we did, and once we know it, we know the cells. Once we know the cells, we know the corresponding string elements, and ADH is our answer. That is how we are going to print it. But that's not the aim. What I want to do next is quickly shift to my editor and implement the program so that we have a crystal clear understanding. So on my editor, I have LCS function, that is longest common subsequence. In it, I'm going to place my code. That is, first of all, I'm going to do m is equal to length of the string 1, n is equal to length of the string 2. And now I'm going to develop or initialize or create my dynamic programming array, dp array. I'm going to name it LCS, longest common subsequence, and it is going to be containing none because it is empty, white space when we start with it, and its length is n plus 1 along columns and m plus 1 along row. So it has m plus 1 rows and n plus 1 columns, starting with 0. So for I in range, m plus 1, and for j in range, n plus 1. I'm iterating in a row-wise fashion. In each row, I'm going to iterate row by row, and in each row, I'm going to iterate each column first. So if any one of the element is 0, since we are using one indexing as we saw, so if any of the index is 0, either I or j, we want the element to be 0. And if that's not the case, we are ready to apply or put our logic in the form of if statement. So if string I minus 1 is I minus 1, because we are playing one indexing on the table, we have to minus 1 when we talk about strings. So if I minus 1 is a match of j minus 1 string, so if the strings are matching, we want LCS ij is equal to LCS I minus 1 diagonally upwards j minus 1 plus 1. And if the strings are not matching, the only case we have is we are supposed to take the maximum of what is placed above it or what is placed to the left of it. So what is the code for it? LCS ij is equal to LCS I minus 1 j and LCS ij minus 1 maximum of the two. So max LCS I minus 1 j, LCS ij minus 1. So getting out of our O of n square loop, what we want is we want to return the last element at the bottom right of the table, that is m comma n. And now I'm going to print it. I've kept string 1 is equal to string 2, so the longest common subsequence should be of length of string because both are matching completely, that is 6. Now to test something different, what I'm going to do is I'm going to take the example that we took on the whiteboard to understand the problem. So instead of keeping both the strings same, I'm going to change the string 2 so that it matches our example that we took on the whiteboard, and I'm going to run the program and it should return 3 according to what we saw theoretically, and it does as well. So that's it. We are pretty much done with this problem with this.